When we prove that every Riemann-Roch space is a finite dimensional vector space, we use the fact that for every positive divisor, its dimension and degree satisfies this inequality. And now we will show that in this inequality holds for every divisor which has positive degree, a slightly stronger version. And to show that, so that means every divisor with positive degree, its dimension and the degree satisfies this inequality, we can suppose that, we can assume that L of A is bigger than 1, because if L of A, the dimension of course should be a positive integer, and in the case when the dimension is equal to 0, there is nothing to show because we suppose that degree is positive and 0 is always less than or equal to this quantity. And for this purpose, we can suppose that the dimension is strictly bigger than 0. And by remark 1.5, this is the trick we often use. We know the existence of the positive divisor, which is equivalent to given divisor A. And for the equivalent divisors in corollary 1 for 12, we conclude that they have the same dimension and they have the same degree. So that means since A prime is a positive divisor, by this fact, we know that its dimension is less than or equal to its degree plus 1. And thanks to the equality of the degrees and the dimensions of A and A prime, we get the desired, and we see that this inequality holds for every positive degree divisor. Now, this is obviously in this case, and we also know that when the degree is negative, dimension is 0, and this is always an upper bound for dimension. Still, we didn't estimate or we didn't give exact computation how to find the exact dimension. But for the moment, let me point out if we have a lower bound in this case, and the next proposition will be answer for that. So that means we will see that there's a constant gamma, this is an integer, such that for all divisors, we have degree A minus dimension of A less than or equal to this gamma. And here note that this obviously gives a lower bound, again in terms of its degree, and here the gamma will be some constant which is independent of the divisor, because this is a stronger version and we want to see it holds for every divisor, and this gamma only depends on the extension degree, or the let me say more generally, it depends on the function field f, and independent of the choice of the divisor A. In order to prove that, first let me remind, for two divisors A1 and A2, one is bigger than or equal to the other one. By lemma 1.4.a, we know that L of A1 is a subspace of the L of A2, and the quotient the dimension of the quotient space is bounded above the difference of their degrees. And if you compute the dimension of the S space, and if you use the notation lowercase l for the dimension, we see that for such divisors, this is A1, such divisors, their degrees and dimensions satisfies this inequality. Let me denote this expression by star. On the other hand, let me consider a non-constant function. For instance, if you consider your function field over k of x with transcendental x, you may continue to use the notation x instead of f, but it holds for any transcendental, so let me continue with the notation f. And for this transcendental, let me consider the specific divisor, so that means it's pole divisor, and we will denote it by b. And for this transcendental, let me suppose that the extension degree is n. So like in the theorem, like in the proof of the theorem 1.4.11, we can consider a basis u1 up to un of f over kf. And with respect to these basis elements, we can choose a positive divisor such that the principal divisors of these functions in the basis bounded above minus d. So by this setting, as I mentioned before, like in the theorem 1.4.11, if you consider the divisor for any positive integer natural number s, we see that f to the I, u to the j's belong to the S space of Sb plus c. And we know that these functions are linearly independent over the base field k of f. We can conclude that the dimension of the divisor Sb plus c is bounded below the number of these linearly independent vectors. So in this case, A is from 0 to S, J is from 1 to n. That means we have S plus n times 1 linearly independent vector in the A space of Sb plus c, and its dimension bounded below this quantity. And here also, let me mention that as we have proven in the previous lecture, this extension degree indeed equal to the degree of the pole divisor or the zero divisor of f, so that means degree of b. So instead of n, let me replace the notation by degree of b. N is the extension degree of k of f, which is also equal to the degree of the pole divisor. So that means S plus 1 times degree of B is less than or equal to the dimension of the space. And for the divisor SP plus C, we know that it is bigger than or equal to its component SP, because we know that the pole divisor is always positive divisor, and we have considered this as a natural number. And C's also have chosen as positive divisors. Again, by lemma 1.4.8, we know that the difference between their dimensions is bounded above the difference of their degrees. This gives us degree C. Or more precisely, let me remove this minus term to the right hand side, and we get an upper bound for the dimension of the divisor SP plus B. So with respect to, if you compare this lower bound and upper bound, so that means the integer which is on the left hand side is less than or equal to dimension of SP plus degree C. And by rearranging these equations, so let me write it. This S times degree B plus degree B, and let me remove this degree C to the left hand side, and L of SP. So here maybe it's better to write the terms that contains S together. So S times degree B minus L of SP, or directly we may write degree of SP, they are the same, is less than or equal to degree C minus degree B. So since the degree B is the degree of the pole divisor F infinity, and this is the extension degree, and this term is independent of the choice of the S, so it holds for any S, we can suppose that this constant is the desired constant we want. That means briefly we have shown that for all positive natural numbers, there exists the constant gamma such that with the divisors in spatial form, like SP or S times pole divisor F infinity, we have the desired equality, the desired inequality. Let me show it by double star. However, in order to complete this statement, we want to see that indeed this inequality holds for every divisor A,